This is Josh White with JW Math Tutoring. In today's video, I'm going to go through Digital SAT Linear Paper Test number 10, the math section modules 1 and 2, specifically the unique questions that do not appear on any of the Bluebook practice tests. So let's go ahead and get started.
But life is a dream that calculus could never predict.
First, before, go ahead and cover these linear non-adaptive paper practice test 10 unique questions. Just want to mention a couple things. First, of course, if you like this video, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. Second, as I mentioned in the other videos covering these linear paper test unique problems, these are the questions from the linear non-adaptive paper practice tests which do not overlap with the Bluebook practice test questions. Okay, so completing these questions, going through these questions will not affect any Bluebook practice tests that you may take. So in other words, you're not going to ruin your score on a Bluebook practice test by completing these questions because these don't overlap. You know, most of the questions do overlap, but these are the ones specifically that do not. All right. That's why I call these the unique questions. In other words, these questions only appear on these linear paper practice tests. They do not appear in any of the Bluebook app questions. All right, so with that being said, let's go ahead and get started. We're going to go through both modules, starting with Module 1 and then moving on to Module 2. First question, we just have a graph of a system of linear equations. What is the solution to this? Well, hopefully you can see on the graph right here, it is the point 4 comma negative 5. It is the point where they intersect. Correct answer is letter A. Moving on to the next page, question number 4. Here we have a graph of a parabola, quadratic function, and we're shifting the entire graph up 4 units. So what is the result? So notice the vertex, which is right here at 2, negative 2, is going to be shifted up 4 units. So the new vertex is going to be at 2, comma, positive 2, because negative 2 plus 4 is positive 2. Basically, it's just going to go, straight up here. Look something like that. So when we go down and look at these various answer choices, all right, hopefully you recognize, again, this one is going to be letter A. It is not going to be B, it is not going to be C, it's not going to be D. Now, technically for this one, you could go to Desmos and you could type in, you could get 3 points from this graph, well technically 1 point plus the vertex, and you could get the equation from the graph, and then you could shift that up 2 units, and then you could look at the graph that you get, and then you could compare it to all these. But I think for a problem like this, that's unnecessary. It's too much work. It's so because you're already given the graph. It's so much easier to just take it, shift it up 4 units. Not I said 2 units there, 4 units. And you see it's going to go straight up, and that's obviously going to be graph A. All right, next up we have question number 15. This deals with basically interpretation of a function. So f of 14 equals 1176. Okay, so notice here W is the letter inside the parentheses. That means the number inside the parentheses will have to correspond to that. So that means that W, or the width, equals 14. So therefore, as we're looking through our answer choices, if we needed to have the width of the rectangle equaling 14. Okay, so that's true for A and B. It is not true for C and D, so get rid of those. All right, then the number that it's equal to, i.e. the output of this function, well, it says here the function f of w gives the area. So that means that this number, this 1176, is an area. So now when we look at the answer choices, okay, it's obviously going to be A because A is the one that says the area is 1176, whereas B says the length of the rectangle is 776, which is wrong. So correct answer for this one is letter A. All right, number 17. Here we have a problem. You're given 3 points. They tell you it's an exponential relationship, and they want to know which of these represents this relationship. Okay, so there's multiple ways you could do this. I'm actually going to show 3 different methods. Okay, method 1 is to basically be familiar with like the theoretical setup for an exponential function. So if you think about it, think about like a b to the x. A out here is your initial amount or starting amount, and that is going to be 1.23. In other words, that's the amount that you get when x is equal to 0. So the function must have 1.23 in the front. So right off the bat, these two are gone. Now, also notice the values, the y values here, h of x values, are increasing. Therefore, that means that the b in here must be greater than 1. Okay? So the only answer choice that meets both those criteria is letter D. And you technically don't have to figure out, determine that it's technically 1.12 as the base here for B in order to get that answer. Now, method 2, excuse me, we could go to Desmos and we could do just a regression on the points and get the answer that way. So we go to table. I'm going to enter all the points in, although technically you only need 2 of them. And then we'll click the automatic regression button. We will go to exponential. Okay, and so here we get our answer. It's 1.22809 and then times 1.12092 to the x. So notice it isn't exact. It's not 1.23 and 1.12. That's most likely because these y values technically have been rounded. Like the actual exact numbers are probably, have more decimal places, but they just rounded it off for this problem. But you can clearly see the only one that is close to the values we get here is, again, answer choice D. Okay, so again, this is how you could do the entire thing in Desmos just by doing exponential regression. Now, a third approach you could also take is you could just plug in points from the graph, or from the table, excuse me. So like, for example, I'm going to do h of 2, okay? I'm going to see, do I get 1.54? So for answer choice A, the answer is no. What about if I do this? Do I get 1.54? No. Answer choice B is wrong. What about now if I do this? For answer choice C, that is wrong. Okay, now what about if I switch to answer choice D by just putting a 1 here? Okay, notice I get 1.542912. This is what I was saying about the rounding before. So yes, this matches. X is 2, the Y or the output is 1.54. So that just confirms that letter D is correct. So that's a third method you could use. Again, you're just basically back solving by plugging in the given point values to see which answer choice, which function gives you the matching value. All right, next up, number 19. Actually, zoom in here, it's a little small. Okay, so here we have an inequality. We want to know which of these tables of values is going to be correct for this one. So, a couple things. If you wanted to do this by hand, I would start with 3, and I would plug that in for x. And then multiply it through 5 times 3, 15 plus 8. Okay, so I see that the y value when x is 3 has to be less than 21 in order to be a solution. Okay, that means this is out because 25 is not less than 21, and also D is out because 21 is not less than 21. It's equal to it, but it's not less than it. Okay, and then we could go to 5, and you could just see 5 times 5 plus 6, 25 plus 6. The y value must be less than 31. So this one is less than 31. This 35 is not less than 31. Cross this out. It is going to be answer choice A. However, you could easily solve this in Desmos as well. So let's just get rid of this. Let's type inequality and let's basically start with some points. All right, so first I'm going to move this over, zoom out. Okay, so notice 317 is a solution. So that means, for example, you would keep A and B so far, but if you wanted to check C, you could notice 325, not a solution, and 321, notice it's on the boundary, but because it's dashed, strictly less than, 321 is not a solution. So far I've eliminated C and D. Now, you could go to the 5 point, and you could do 527. Is that a solution? Yes. What about 535? Notice no, it is not a solution. It's not in the shaded area. So that could allow you to eliminate B. And again, you'd be left with answer choice A, the same thing I found, solving it by hand. So that's how you could do the entire thing in Desmos. Again, each of these methods, completely acceptable. All right, let's look at 22 now. So basically, the floor of a ballroom has an area of 600 square meters, and there's a scale model. The length of each side in the model is 1 times the length of the corresponding side of the actual floor. What is the area in square meters of the model? Okay, so the theoretical way that you do this, or you figure it out, is you take the 600 square feet and you basically multiply it by 1/10 twice, or 1/10 squared. The reason you do that is because essentially the scale factor from this would be from large to small, from actual to the model, is basically times 1/10, but that's for one side. It says the length of each side is 1/10. So that's the scale factor. Therefore the area factor is equal to the square of the scale factor, for any two-dimensional thing. Or I guess technically for three-dimensionals as well if you're talking about surface area. So that means the ratio of the areas is going to be equal to the scale factor squared. That's the 1/10 squared, or basically 1 over 100. That means the area of the small is going to be 1/100th of the area of the large, which is 600. So it's 600 times 1 over 100, which is just 6. So the correct answer for this is letter A. Now, if that's a little confusing, let's pick some actual numbers and work it out that way instead. So for example, I'm going to say that the actual has, let's say, a length of 60 and a width of 10. Okay, that gives me an area of 600, so that checks. That would mean for the model, since each side is 1/10, the length of these, that would mean that this side is 1, 1/10 of 10 is 1, and that would mean that this side is 6. So what's the actual area of the model? Well, 1 times 6 is 6. So we get the same answer. Again, it might be easier to think of it this way when you're using actual numbers instead of, like this scale factor and area factor and so on. So if you want to do it that way, totally fine as well. All right, let's look at 25 now. We're increasing a quantity X by 1800%, and the result is 684. What is the value of X? So first I'll show you kind of like what I would say the traditional way, then I'll show you how you could back solve it, and then we'll look at possibly a Desmos solution. So first of all, the actual equation you're going to set up, okay, you have the original quantity, then you're increasing by 1800%. So 1800% is equivalent to 18 as a decimal. In other words, you're taking 18 times the original quantity, and this is how much you're increasing it by. So we have original and then the amount of the increase, and that equals 684. So you basically just solve this equation, and you get the original number turns out to be 36. Correct answer is D. Now, you could also back solve this, and by that I mean you start with the answer choices. So like you take 12,996. Okay, and then you take 1800% of 12. Actually, let me see if I can do it this way. I'm not going to use X because X is a defined thing. I'm just going to use A instead. So here's what we're looking at. The reason I'm doing this is just to save time. So are all my answer choice. A is my answer choice I'm plugging in. So I'm taking the number, I'm increasing it by 1800% of that, and then I'm seeing, do I get 684? Okay, the answer is obviously no. So now let's try answer choice B. Do I get 684? No. Now let's try answer choice C. Do I get 684? No, it's much closer. It's 722, but it is not 684. So let's check D. So right here, we have the correct answer. Basically, the number increased by 1800% of the number, and therefore we get the actual value. Now in Desmos, we should also be able Let's see if we can actually use, here's how you could actually use x and set up an equation just all in one step. So you could say x being increased by 1800% of x is 684. All right, so that I basically just translated the text into an equation, and now on my graph, notice there's a vertical line right here at 36. So this is how you could, again, just basically take the whole thing, even with the percentage in there, you don't even need to convert it to a decimal, and get the correct answer as well. All right, so now let's move on to module number 2. This one only has 3 questions, so we'll be through this pretty quickly. The first one here, what's the best interpretation of the 4 in this linear function, linear equation? So the 4 is the y-intercept value, or your initial amount. Therefore, the correct answer for this is going to be D. It's the height of the tree when it was first measured. Like, none of these others make sense in terms of a y-intercept or, value or starting value. All right, let's look at number 11 here. So you have an equilateral triangle S. Here's equilateral triangle S. And then you multiply it by scale factor to create an equilateral triangle T. So here's S, here's T. Okay, scale factor we're multiplying by is just K. All right, the length of each side of T is greater than the length of each side of S. Which of the following could be the value of K? Well, if the sides are getting bigger, from S to T, that means you have to multiply by a number which is greater than 1. That's the only way you're going to make a number bigger. If the number is less than, obviously it's not 0, because if you multiply by 0, then your answer is just 0 and triangle wouldn't exist. But if you multiply by a number less than 1, then T is going to be smaller. The sides are going to be smaller for each of them. If you multiply by exactly 1, then the two triangles are basically going to be congruent. It's going to be, T is going to be the exact same size as S, which does not meet the conditions of the problem. It says the length of each side of T is greater than the length of each side of S. So the correct answer for this one just has to be A. Again, the K value just has to be greater than 1 to make the sides larger, so it's just A, which is the only number greater than 1. All right, lastly, number 22, we have an absolute value equation. They want to know the sum of the solutions to this. So first, I will show you how you could do this by hand. Then I will show you the Desmos method. Desmos method is probably the quicker way to do it, to be honest, but still, absolute value equation, you set up 2 separate equations. The first one looks like the original problem, no absolute value signs. The second one, you set equal to the opposite of the number or expression on the right side. So now you solve each of these, which is going to be minus 13 on both sides. Okay, so we should get 60 in the first one. We should get negative 86 in the second one. Just checking my notes. Now we divide by negative 5 on both sides. Okay, what do we get? We get negative 12 and we get positive 86 over 5. So we got to add these two numbers together. Of course, you could just go to Desmos and do this, but just in the interest of reviewing fractions, this is over 1, so I'm going to do times 5 times 5. So I get negative 60 over 5. Notice it actually would have been easier if I had not simplified it and just kept it like this and just added these two together right here, because now you can just see it's 60 plus negative 86, or 60 minus 86, which is negative 26 over 5. Why am I getting negative instead of, oh, never mind. I just realized what the mistake was. Sorry, this is the one that's negative. This one is positive right here. It should really be these, point to these two that I'm adding. Negative 60 plus 86. It's positive 26 over 5. Just checking my notes. The correct answer is letter D. But now let's see how you could do this entire problem in Desmos. So let's delete this. Now, I prefer for absolute values to solve them by doing y equals left side, y equals right side, rather than typing the entire equation in just one line, because you can't click on the lines when you do that. So I think it's preferable to do this method, and then see now I can actually click and I can like, okay, so let's export this and let's export this. So now my two values are going to be -12 plus 17.2. Okay, and so I get 5.2 as my answer. Now notice all the answers are in fraction form, so all you have to do is just this right here, and now it's 26/5. Now it matches. Okay. One other thing I would just mention on this problem, you could of course use regression to solve this. And the way I would do that, 1 equals, there we go. Okay, so notice we have our first answer, right? X1 is equal to 12. Now what I'm going to do is I'm going to type it a second time. It's giving me the same answer. So what I have to do is I'm going to put in a condition here at the end. And notice I used x2 instead of x1 because I want x1 and x2 to be my two solutions. So now what I'm going to do is I'm going to make it less than 12. And notice here is how I get the second answer. Okay, so I have one answer is x1. I have the other answer is x2. So what's the sum of them? x1 plus x2. Okay, why did it just, something just happened. It had the -17.2 and then it changed for some reason when I clicked around. So let's try this again. Let's put in the condition. See there? Okay, let's x1 plus x2. Okay, now it's working. You can see there I get my two distinct answers, 12 and -17.2, which is the 86 over. Oh wait, sorry, no, mistake. Mistake, start over. That should be negative. That should be negative. Now we have the positive answer of 17.2. We have the negative answer of -12. We add those together. We get positive 5.2. We click on that, 26.5. So again, all I'm demonstrating here is this is how you could take the absolute value equation. You could solve it using regression and um, basically do two different regression statements, and you have to put a condition thing on one. See, again, it for some reason it just like messed up. It just changes x2 to the same answer. I don't know why. So let's do this. Yeah, see now it's back. Putting this condition, now it's back. I don't know why it keeps changing the answer for the second regression when you click around. It shouldn't, but in any case, now we have our two unique answers. We add them together, we get 26.5. So that's just an alternate method you could use to solve it as well. Anyways, that took a little bit longer than expected, but these are the unique questions from Linear Non-Adaptive Paper Practice Test number 10. So I hope you enjoyed this video. If you have any questions or comments, please do leave them below. Otherwise, if you did like this video, please do give it a thumbs up, subscribe to my channel, and sign up for notifications. Also, be on the lookout for the solutions to the unique questions from the other linear paper practice tests. So far, I've got 7 through 10 up, and I'm going to work backwards on the older ones as well. And lastly, again, if you are looking to improve your knowledge of Desmos, please check out my Ultimate Desmos Guide to Digital SAT Math. Over 3.5 hours of tips and tricks and instruction and 45 practice problems to help you improve your knowledge of Desmos.